not a great picture, but what this has is all the important values, right? Like I can tell you precisely where you're having changes in concavity. I can tell you that from here to here it looks like this shape. And this is the way we used to do it, like we humans. This is the way we used to graph things by hand. And this is an easy function, right? But imagine a more complicated function, right? Something much more complicated. How bad this could be. But we didn't have the technology we have nowadays. So I believe that as long as you understand how to actually come up with all the, where it goes up, down, where it's concave up, concave down, if you can do all that, then this part we really don't need to do by hand. That's just my opinion. That's why I don't get deep into this. But at least I've shown you one. Do we need to look at the computer to verify it? Y'all believe that's what it looks like? Okay. All right. So I'm going to offer a quick little bonus, all right, right now. Tear out a piece of paper. It's a bonus, not a quiz. It's a bonus if you're interested. Put your name on it. It's timed. You only get like a minute to do it, all right? And I want you to do your own work, okay, because I'm going to ask you to draw me something. And so it'd be very easy to just kind of look at your neighbors and draw what they draw, all right? So I want your eyes on your own paper for this. Can we do that? I would hate to give a bonus and then you get caught cheating on the bonus and then you get in trouble, right? Here we go. So I'm going to give you some conditions for a function. You're going to see if you can draw it. All right, so here's the first condition. So I want you to sketch me this function f, all right? And here are the conditions on f. First condition, f of 3 is equal to 4. The second condition is that f prime of x is greater than 0 on the interval 0, 3. And the third condition is that f prime of x is less than 0 on the interval 3. You know what? Make this not 0, 3. Make it negative infinity to 3. Sorry. And then from 3 to infinity, its derivative is less than 0. And the fourth and final condition is that f double prime of x is greater than 0 on this interval. There you go. Look at it, think about it. And if you got something, draw it, fold it up, hand it to me. It's a bonus, so don't stress out about it. You got something?
No, it's right, but it feels right.
Feels right? Do you want me to look?
Yeah.
You want me to look? That's right. Good. We'll go 30 more seconds. $20. Okay. We're getting close on time here. I'm going to give you 10 seconds. Okay. Thank you. Your names are on these, yes? All right, last call. Anybody? Oh, so everyone's turning something in? Okay. You drew something? You don't have to turn something in if you didn't get anything. Anyone else? All right, if no one else, right? No? Oh, okay. Okay. All right. So let's just talk about this real quick. That's it, right? This just means that you have a point on the graph, right? So that just means that at 3, you have to be up here at 4, right? Dot. Done. Easy part. All right, this means that, tell me in layman's terms. The graph is increasing. So when you're to the left of 3, it's going up. So the graph's got to be going up here, right? And then this is saying you have to be going down, right? This is saying that you must always be concave up. Yeah, so a lot of people will try and do this. And yes, it goes up and then down, but see, this is concave down because it looks like a frown. It has to look like a smile. And so a lot of people struggle with that because they're like, how am I going to draw a smile? Like that. You see? You could do various things. There's a couple of different variations of that, but that's the idea, all right? So if you got it, good. If you didn't, no big deal. But now, hopefully you see that. It is possible to go up and then down and not have to be concave down. You could be concave up. Let me ask you another question while we've got this picture up here. What's the derivative of this function at 3? It doesn't exist, right? At 3, the derivative doesn't exist because you have corner or cusp or something like that, right? All right, very good. We're ready to move on. We are, I am. All right, we have reached the other part of this class that involves word problems. And so naturally, students don't like these, but hey, you know, this is 4.5, yep. I don't know if this is going to be on the next test on Thursday. Pardon me?
Is anything that we learned from now on?
Let's just see how this goes. We have an hour, right? So let's see how this goes. I know that a lot of you aren't going to want this on this test, but then it's going to be on the final. I mean, you're going to be tested on at some point. Let's do a few problems first. Maybe I give you a basic one on the test. One that's just like, do you understand the basic idea? As opposed to something, pardon? The final will probably not be like fully comprehensive. Like, I'm not going to go back and, like, I wouldn't ask you to go and show me how to do chain rule again. Like, here's a bunch of chain rule problems, because if I ask you to go figure out where graph's going up and down, then you're going to have to do derivatives, and I can just make sure to get chain rule in there. You know what I mean? It's like built into other problems. So it won't be completely comprehensive. All right, so optimization. So I want to start, before I show you the notes or like, you know, any sort of like guidance on this, I want you all to think about, whoa, why did I do that? I want you all to think about this. Let's say that I give you a string, okay? You have this string. Of course, the string is flexible, right? So you can bend it, move it around. Let's say I give you this string, and let me tell you that string is 20 feet long, okay? Pretty long piece of string. And I want you to take that string and I want you to lay it on the ground. I want you to make a rectangle out of that string on the ground, right? I know it won't be a perfect rectangle, but let's just say theoretically you could make perfect corners with the string, bend it, right? I want you to lay it on the ground and make a rectangle out of that string. There's a lot of different ways you could do this, yes? Now I want it to be a rectangle. We all need to understand what a rectangle means. Like these two sides are the same length, these two sides are the same length. These are right angles, okay? And in this particular scenario, we are going to say that a square is one special type of rectangle. So you could possibly do a square. All right, so my question to you is, everyone can make their own rectangle however they want, right? I would like to talk about the area of the rectangle that you make out of this string. Okay, think about the area in here. You're going to do your string one way, right? You're going to do yours another way, yours another way, right? Regardless of how every student here does this with their string, will we get the same area regardless of what they do? What do you all think? Just think about it for a second, and then let's contemplate it more. Before you think, if we're all using 20 feet of string, and everyone makes their own rectangle, should I be able to go around and get the same area for each of these people's rectangles? So show of hands, how many of you think we should all get the same area regardless of how we make the rectangle? How many of you think it matters? It's about half and half. Well, there's an easy way to settle this. Let's just draw a couple of scenarios, all right? How about this scenario? How about somebody does this rectangle where this is 6 feet here and 6 feet here. I've used how much? 12? How much do I have left? 8. So each of the other sides has to be 4 feet and 4 feet, right? What's the area of this rectangle? 24, right? So the area of this one is 24. All right? You want to go 5 by 5? So I can go 5 by 5 by 5 by 5. That's a square. Okay? Is that using all 20 feet? Yes? What's the area of that? 25. This one's better, yes? I mean, better if your goal is to get more area, that one's better, right? All right, let's do another scenario. Could I have done this? How about this scenario where I go, I don't know, 8 and 8? The other sides would have to be 2 and 2, right? And you would have an area of 16. See, we're all using the same amount of string, right? So we all have the same perimeter, don't we? We have the same perimeter, but we're not getting the same areas. Yeah? Is there a limit to how long I can make my rectangle?
Yes.
Yeah, there is. What's the limit to how long I can make my rectangle? 9. So I'm hearing 9, I'm hearing 10. What do y'all think? Could I do 9.5?
Extremely close to 10.
I can go up to 10. So let's take this extreme. What if I do 9.9 and then the other side is 9.9? Then how much do I have left over for the other two sides? I have, what is that together? 18, 9, what is that? That's 19 point. Come on, Em. 19.8, right? That's 19.8, right? That's 19.8. So you have how much left over? 0.2, so 0.1 on each side? Yes? So I could do that, yes? And then the area of that, when someone do that, 9.9 times 0.1, you only get what? What's the area of that? It's small. 0.99. So if I go 9.9 feet, the other side 9.9 feet, and then across just 0.1, I get a really small area, right? But I've used all of the perimeter, yes? So the question, back to the question, how long can I make this side? Could I make it 10? We as a class need to establish whether or not we're okay with this. Could I do 10 here and 10 here? And that would leave me how much for the other sides? 0. Which wouldn't really be a rectangle, would it? Right? But 10 would be the absolute extreme case, right? This would be the absolute extreme case where this is really almost just like an area of 0, wouldn't it be? It would almost be like you took your 20-foot string, you cut it in half, and you just made 2 sides, and you didn't have anything left over to make the rest of the rectangle, right? So the absolute extreme on one end would be to make that length 10, right? And that would force the other side to be 0. So what we're interested in here with these problems, which are called optimization problems, are problems like this, where initially, at least half of you thought that we were going to get the same area no matter how we did it, right? We do get different areas. So the question becomes, how do we do it to get the most area, right? It looks like from our analysis of just trying some different examples, what looks like the best scenario for us? A square. It looks like that's the best case, right? But how do we prove that mathematically? Because you would have to go check every other possibility, right? Check 8, check 6. I'd have to check 5.5, 5.25, check everything, right? And it's impossible to check everything because there are an infinite number of numbers to check, right? Yeah, this is exactly like the river and the buildings, which was kind of a preview into how we use what we've just learned about figuring out where things go up and down, right? So here's how we're going to approach this. Are we all sold on the idea? Hopefully you're sold on the idea that it actually does matter. The area is dependent on how we draw the rectangle, right? Okay, so let's now frame this problem more in a general sense. We have 20 feet of string, all right? Here's the question, the way it's going to appear to you in like a test. You have 20 feet of string. Find the dimensions of the rectangle formed by this string, or formed, by the string, which has a maximum area. So I'm giving you 20 feet of string, and I want you to find the dimensions of the rectangle formed by that string, which will give you a maximum area. Okay? So just reading the problem, what am I asking you for? The what? Find the dimensions, right? So at the end of this, our answer maybe will be 5 by 5 or something like that. I want to know what the dimensions need to be so that when I make a rectangle out of this string, I get the biggest area possible, right? To start this problem out, what I'm going to do is I'm going to write down what's called the objective. The objective of this problem is to find the maximum area, to maximize the area, right? We have this rectangle. We want to somehow figure out what its dimensions are in order to maximize the area, right? So that's the objective. Maximize the area. That's the objective. So that means that I need to come up with an equation that has area in it. I need to find some way to represent area mathematically. And we know the area of a rectangle is what? Length times width. Like if we draw a rectangle, if I draw a picture that goes with this, that's my string laying on the ground. We can call this L and this W, right? And then we know that the area is length times width. Is that all straightforward so far? We want to find the most area, the maximum area possible. So we write down a formula for the area of a rectangle and we draw a picture to go along with it. Now, right now, do you agree that the area depends on two different variables? It depends on what the length and the width is. I would like to see if there's any way I can get that area to depend on one variable. This is like the river problem. Remember on the river problem from last class we said we're going to go down the river and then across? And what we did is we found a way to turn that into a function of one variable and then we graphed it. We're going to see if we can't turn this area into a function of one thing and one thing only. And if we can do that, then we can do the calculus. So now we need to somehow come up with a way to get this to have just either L's in it or W's. And to do that, I'm going to bring in the next part of these problems, which is called the constraint. The constraint. The constraint of this problem is that I only have 20 feet of string, right? I only have 20 feet of string. So when I build this, I have a restriction on the perimeter, don't I? The perimeter, the distance around it. The perimeter of this must be 20, right? The perimeter must be 20 feet. But what is the perimeter of that? You know, by definition, what is the perimeter of this in terms of L and W? 2L plus 2W, right? 2L plus 2W must equal 20. Right? So all I'm doing is I'm rewriting perimeter in terms of what it is, right? To go around this thing, you'd have to go 2L's plus 2W's. So I've got the thing I'm trying to, the objective, the thing I'm trying to maximize is here. And right now I can't do any calculus because I have two variables. I needed to get to one variable. The constraint allows me to create an equation. That equation has my two variables in it, right? So I can solve that equation for either L or W, my choice, your choice. So would you like me to solve that for L or W? L? Okay, so I'm going to solve this for L. Let's divide everything by 2 first. Is that all right with you? Divide everything by 2. And now let's solve for L, so subtract W. And that's an equation for L in terms of W. Take that and plug that in up here. So the area is now L, but we just said L was 10 minus W times W. Now, is the area in terms of a single variable? Does the area depend on one thing? Yes, W, right? That's all it depends on. So I'm going to write this as A of W, like a function. A of W equals, and I'm going to distribute this through, 10W minus W squared. And this, everybody, is what we're trying to do here. We're trying to take a word problem, and we're trying to somehow figure out a maximum value of something. We know from what we've been studying that we can find maximums and minimums of things, but they have to be functions of a single variable. And we have somehow turned this word problem into a function of a single variable. Do y'all see that? I just need now to talk about its domain. This is a critical step. We have a function, don't we? Does it have a domain? Remember, there are two different methods we've learned, right? Closed interval method and open interval method. We use the closed interval method when our domain is closed. We use the open interval method when our domain is unrestricted. Is our domain restricted here or not? Yes. I'm hearing yeses and nos. If it's a yes, why is it restricted? There's a smallest and largest value for W, isn't there? It's like the extreme cases. What are the extreme cases we said? 0, right? If W is 0, then you don't have a rectangle, but we can say that's an extreme. And then the other extreme would be W is 10. And then you're leaving no length, or there's nothing left. Like if W is 0, then you're not going to have a rectangle, but that's the full extreme case. The other extreme is that W is 10, and then you don't have anything left for L. Yes?
So is that 10 because of that extreme, or is that just a coincidence?
I would say it's more of a coincidence. It's not going to always be that number. So my domain here is I've got this on the closed interval 0 to 10. Why is it not 0 to 20? Yeah, well, you have to have two sides, right? If I said W is 20, then you've got to build me this and this, right? And that means you need 40. You need 40 feet of rope, or string. You don't have 40 feet, right? You only have 20. So if I say W is 10, I can make that 10 and that 10. That leaves me nothing for the other sides. That would be an extreme. But to say this is 20, that implies that you have 40 feet of rope or string and you don't have that, okay? All right, so do we have a continuous function on a closed interval? Yes. Can we find the maximum of that? Absolutely. So I'm now going to use the closed interval method. So this is a continuous function on a closed interval. So I'm going to use the closed interval method. Do you remember how to do it? What do you do for closed interval method? Find the derivative. Okay, let's do that. Take derivative. A prime of w is easy derivative. No? Yeah? Yeah? What's the derivative of that? 10 minus 2w. Okay, what do you do with that derivative? Critical numbers. So same thing we've been doing, right? Still find the critical numbers. So to find the critical numbers of that, set that equal to 0. Where's this derivative equal to 0? Well, that's pretty straightforward. 10 minus 2w equals 0. Solve that, you'll get w is 5. Is w in the domain of the original function? Yes, between 0 and 10, isn't it? Okay, good. Yeah, one more thing. We also have to check where the derivative doesn't exist, right? But look at the derivative. It's nice, isn't it? So you don't have that issue. Yes, what's your question?
So this is what I was asking you about last time.
Oh, okay.
So this step here where you're looking for where it doesn't exist.
Uh-huh.
So I think what you're saying is you take every number that's in the domain and you plug it in.
No, what I'm doing is I'm taking a look at this as if it's its own function. Like forget the original one. Just look at that. Is there anything you can't plug into this?
When you say you can't, what do you mean?
Can't.
Yeah. What do you mean by?
If you plug in a number here, are you ever going to have a problem like division by 0 or square root of a negative number? Anything that you wouldn't be able to give me an answer?
So this doesn't even matter because there's no fraction.
That's right. It's a polynomial. Anytime we see a polynomial, domain's everything, which means we don't have a problem. If this would have been, well, I'll do another example. You'll see we'll have some things to worry about. You good? Everyone good? Okay, what do we do? This is where things are different from today.
Plug in your 2 points.
You plug in these 2 points and this point into the original function. You don't do a number line in test points. All you do right now is you inspect what's a of 5, what's a of 0, and what's a of 10. See, the closed interval method says that, look, if you've got a continuous function on a closed interval, that you've got to reach a highest and lowest point. And it's either going to be at the endpoints or it's going to be at a critical number. And so we found the critical number. We know the endpoints. We're going to evaluate the function at these things. And then whichever is the biggest answer is going to be the maximum. So plug 5 into this. What do you get if you plug 5 into that? 50 minus 20. So you get 25, right? What happens if you plug 0 into that? 0. And if you plug in 10, you get 0 as well. So what's our maximum value? 25. And that was the 5 by 5, wasn't it? So we have a maximum value here, right? We have a maximum value here. But we have not answered the question. The question was, what are the dimensions, right? What are the dimensions of the rectangle?
Real quick,
Yeah, yeah.
we plugged it into the original.
Original.
Not the
A, not A prime. A. So A of that,
Why did you plug into the original?
because we're using the closed interval method, not the open interval method that we've been using today.
Okay.
So this is from last time.
Okay.
Was it last time? Closed interval? Yeah, I think it was last time. So.
Not from what we learned today.
Now, yeah, it's confusing. The open and closed confuse students because you're like, wait a minute, do I plug that into the original or does it go in the derivative and all that? You have to keep track of all that.
So then here we would plug it into the original function, solve for w, and then plug it into a equals L times w, and get the length.
Actually, we can get length right here. Do you see right here? We can get length directly from our constraint. So yes, you could though, but I think you got it right here. All right, have I answered the questions? All right, so we still need to answer the question. The question was to find the dimensions. We know that this is the maximum area you can get, 25. When does it happen? When what? When W is 5, right? So I'm going to start summarizing here. We get a maximum area of 25 square feet. I'm just putting, that's information that I was not even asked for. I'm just stating it. We get a maximum area of 25 square feet when W equals 5 feet and L equals, well, L you get from here, right? If this is L, L is 10 minus W, so what's 10 minus 5? 5, which means that we needed to have made a square, okay? A 5 by 5 square on the ground would give you the maximum area. If you do it any other way, it's going to be less, I promise. That is the optimum solution, which is why this section is called optimization, because what we're doing is we're trying to optimize something, do it the best we possibly can. Any questions?
So on the word problems, you always put it in the original, not the derivative?
No. This problem, we put it into, this problem was closed interval method.
Oh,
This one was.
It'll tell you though, to see.
It won't, the problem, you're going to have to determine it from the problem. Actually, I'm going to do a problem right now because I want you to see that difference, okay? So if there aren't any more questions about this one, I would like, no questions? Okay, I'd like to move on to a similar problem, and we're probably going to know the answer before we do it, but I'm going to show you how the setup is going to need to be different. Okay, so now what I want is this. I want you to find the dimensions of a rectangle with area of, oh my gosh, area of 20 square feet. 20 square feet, which has the smallest perimeter. Now look, these are the first problems we're doing. So some of you are probably going to be able to just like logically deduce what the answer should be without doing any calculus, and that's fine. But there are going to be problems that you can't logically deduce, that you're going to have to run through the actual steps. All right, so I'm going to have a rectangle, right? What's the big difference in this problem from the previous one? I'm giving you an area that has to stay the same, right?